Swayam Prabha. Digital India. Educated India.
See, what I am describing so far and what I will do in the next lecture are all things that happened before 1960. Interesting things happened after 1960, very, very important things. And the first one was instrumentation advance. And it was possible by the implementation of a well-known method called the Fourier transform, for which an experimental setup was first made by Professor Richard Ernst. I think Anderson and Ernst, if I remember. Professor Richard Ernst published the first the Fourier transform spectrometer setup in 1966 or 1967, around that period. And after that, NMR has never looked backwards. The Fourier transform NMR spectrometer, FT NMR is called, which is what we have downstairs in our institution also, several of them. The FT NMR changed the entire magnetic resonance. And a little later, it was a simple experiment. Instead of a steady magnetic field, a magnetic field gradient, that is varying magnetic fields, was introduced by a very famous chemist, Professor P.C. Lauterbur, and later it was also studied by Professor Richard Ernst. And then they used two-dimensional imaging technique with the gradient magnetic field. And that became later the magnetic resonance imaging. It allowed protons with different relaxation times to be captured as images. And one could directly look into objects inside the human body through proton resonances. Around the time that when the image magnetic resonance imaging happened, there was Professor Jenner from Belgium, G-E-E-N-E-R, Jenner, John Jenner, who gave a beautiful talk in one of the conferences.
Sir?
Yes?
Sir, are you sharing the screen, sir?
Not yet, not yet. I'm only telling you stories now.
Okay, sir. Thank you, sir.
I'm only telling stories now.
Okay, sir.
John Jenner introduced a beautiful concept where he said, instead of one frequency spectrometry, spectroscopy, he introduced a two frequency spectroscopy, two variable frequencies and times, and that became later studied. That was very well studied later by Professor Richard Ernst again. And in 1976, he published the first paper of what we call as the two-dimensional nuclear magnetic resonance. The two-dimensional magnetic resonance, among the first of several experiments, separated chemical shift from spin-spin coupling in the spectroscopy. Chemical shift was in one dimension, and spin-spin coupling was in another dimension, the other frequency. And these experiments were later immediately applied in protein research, in understanding amino acids, the proton NMR of amino acids, which are very complicated and very convoluted spectrum. And FT-NMR and two-dimensional FT-NMR were later introduced into the field by Professor Kurt Wuthrich from Germany. And protein NMR today is very, very routine instrument, but very challenging. It's routine in the sense everybody does it. It's not that everybody understands it. The challenging parts of protein NMR continue to And now magnetic resonance imaging has moved to material science. And MRI, of course, has become very, very unique. It is a non-destructive technique in the sense your cells are intact after the experiment. Whereas if you do X-ray, some of the cells are destroyed, so it is not a non-destructive technique. And X-ray you should not be exposed to X-rays as often as we normally do these days, but you have to be careful. So NMR has moved so much. All of this was possible because the quantum mechanical theories of NMR were well ahead of their time. Before the instruments, experiments, and other things happened, the quantum mechanics was very well known. The reason for that is the spins have finite number of energy levels. Spin 1/2, only 2 energy levels. 2 spin 1/2, only 4 energy levels. If it is a spin 1, there are only 3 energy levels. Even if it's a spin 9/2, 9/2, there are only 10 energy levels for a spin 9/2. Yeah, spin 9/2 does exist, except that the gammas are all probably very weak. And they have other effects called nuclear quadrupole resonance, which is an electric property and which shows up as perturbation in the NMR spectroscopy. It starts even with nitrogen, because nitrogen 14 has a very strong electric quadrupole moment, and that does show up in the NMR spectroscopy. That has effects on the spin relaxation times. Quadrupolar systems relax faster than systems without the quadrupole, and dipolar systems, like solids, they relax much slower. And these things are fundamentally very well studied theoretically for many, many years. And NMR spectroscopy techniques and technologies were later adopted in optical spectroscopy, in IR, and in microwave later. NMR came way before all the other techniques and set up the stage for other experimentalists to use the two-dimensional or the Fourier transform methods in optical spectroscopy, like FT-IR spectroscopy, two-dimensional FT-IR spectroscopy, two-dimensional microwave spectroscopy. So it is possible to do these kind of things now. But NMR was the step ahead. And many NMR physicists won Nobel Prizes in other fields after they moved away and set up the experiments in other fields. Several of them won Nobel Prizes. So it's a very fundamental concept. In any case, what we are going to study now is still preliminary lessons. And let us now share the screen. So, now show you the next lesson. Well, I guess it's 4. Not 4, 5. Coupling, spin, coupling. Yes, okay. Yeah, no, we will look at it. I call it 7, but it's a long lecture. Already warning right at the title, it's 7. Okay. We will try to do as much as we can, but then you should read it yourself. Okay. Also. So I did this spin-spin interaction, J coupling, Ramsey and Russell I mentioned the last time. And a first simple 4-step model for the spin-spin coupling. Nucleus 1 is oriented parallel to the applied field, okay, H0. Electron in its immediate vicinity tend to align anti-parallel to minimize the energy. Remember, gamma is negative for the electron. Therefore, anti-parallel means electron also aligns like this, okay, with the field. And so you can see that the electrons align with the nucleus aligned like this. Electron 1 influences the other electron 1, sharing the same bonding molecular orbital orientation. Electron 1, the other electron it influences, and there is a Pauli spin pair according to the principles of Pauli. Okay? The spin pair has to have, they can't be the same orientation, they can't be in the same state. So you can see that the nucleus 2 associated with electron 2 now forming the bond aligns parallel or anti-parallel to the second electron, and determining. So you can see that the nucleus 2 is either this way or that way. The result of this is the splitting of resonance line 1 due to this alignment. It is the electron-mediated influence of two orientations of the spin that results in the spin 1's two splitting energy transition frequencies. Okay. This is a very simple mechanism. The coupling can also occur through two nuclei bonded directly. Okay. Carbon and hydrogen, C13 and hydrogen. This is a weak coupling. Phosphorus 31 and hydrogen. Phosphorus 31 is hydrogen 1 is obviously through bonds of the nuclei. So you can also have H, C, C, H. Even though carbon doesn't contribute to the spin, the electrons mediate the proton coupling. Okay. C12 does not have a magnetic moment, even nucleus. Therefore, in general, spin coupling is through bond and not through space. Multiplet patterns you have already seen, 1:1, 1:1, 1:3:1, 1:4:6. It's also easy to create this table because the entry in the middle is the sum of the two entries on either side of the previous line. So you can see 1 + 3 gives you 4, 1 + 4 gives you 5, 5 and 4 + 6 gives you 10. This is nothing but the Pascal series. This is the Pascal triangle, but this is nothing other than the binomial series. So J coupling involves groups of nuclei that are magnetically equivalent, not just chemically equivalent. Okay, magnetically equivalent is another thing that I need to explain, but let me skip that now. We will assume that that's important. But for example, if you look at the two nucleus, hydrogen and hydrogen in difluoroethylene, fluorine A, fluorine B, you can see that the HA and HB are chemically equivalent. They both have the same electronic surroundings, but they are not magnetically equivalent because HA's interaction with FA versus FB is different from HB's interaction with FA and FB. So you can see that these two are not magnetically equivalent. They have the same evolution. Therefore, HF coupling constant is different from HAFB coupling constant, and HAHB coupling constant is of course different. So you can see that proton with the fluorine does not have the same coupling constant as this proton with this fluorine. Therefore, you can see such systems in which there are 4 nuclei whose chemical shifts are quite far away. Fa and Fb are quite different from HA. They are called A prime, X prime, because H and F are large chemical shift differences. So the two H's are A and A prime, the two fluorines are the X and X prime. Okay. Now, what is the quantum mechanics of the spin coupling? Now comes the mathematics. Sorry, you have to do this, and let us see how we can understand. The Hamiltonian is, now I'm writing only the frequencies. Okay? This is spin 1. There are so many spins. N spins are there, therefore we write spin 1 Z, spin 2 Z, spin 3 Z. Each one has a different chemical shift. Okay? And then the coupling between all the spins is I dot J. It's a scalar coupling of the two spin vectors. But we will use only the Z component here. You can see that. IZ, IJZ is one component. IJX is another component. IY, IJY, that's another component. But we remove the X and Y component in the first order limit because they connect different energy levels. The Zs do not connect different energy levels. They keep the same energy. They are eigenfunctions of the same energy. Therefore, these are called first order interactions. This is what we used qualitatively in the last lecture. So the Hamiltonian for N spins is N chemical shifts and N spin 1/2 Z component, and then N into N minus 1/2. Because you see that there are N i's and N j's, so the total number of coupling constants for a pair is N into N minus 1/2. Now, we can ignore that because we are not going to consider the Jx and Jy terms which are given here. So the first order theory let's look at n equal to 2 spins. So the 2 spins will have the Hamiltonian, the spin 1, Z component with the magnetic field, with the frequency, and this is containing the magnetic field. This is the gamma H naught factor. We have written this as H omega instead of H bar omega naught. So this is H omega. This is nu, H nu. Okay. So this is the chemical shift for spin 1. This is the chemical shift for spin 2, I2, I1Z, and I2Z. And then the coupling between the 2 spins is J times I1Z, I2Z. Now, for perturbation theory, what we do is that we use the 4 energy levels, alpha 1, alpha 2, alpha 1, beta 2, that is spin 1 up, spin 2 down, beta 1, alpha 2, spin 1 down, spin 2 down, and spin 1 and spin 2 both down. Now, if you use this, please remember, I1Z on alpha 1 will give you plus a half, if you remember last lecture of mine. I2Z on alpha 2 will give you plus a half. I1Z on alpha 1 here gives you plus a half, but I2Z on beta 2 gives you a minus a half. Okay? I2Z. I1Z does not change, but I1Z now with beta 1 alpha 2 will give you a minus 1 half. I1Z on beta 1 beta 2 will also give you a minus 1 half. But I2Z will give you for alpha 2 a plus 1 half. And I2Z for beta 1 beta 2 will give you a minus 1 half. So first calculation is Hamiltonian applied to alpha 1 alpha 2. So minus nu 1 by 2 plus I1Z is plus a half. I2Z is also plus a half because it's alpha. So it's minus nu 2 by 2. Now, this is a product of I1Z and I2Z. So plus 1 half into plus 1 half, which gives you J12 by 4 times alpha 1. So this is an eigenfunction. Alpha 1 alpha 2 is an eigenfunction of the spin Hamiltonian. Let's look at alpha 1 beta 2. Now, alpha 1 beta 2 for I1Z will not change. It is minus u1 by 2. But due to I2Z is beta 2, so this is plus u2 by 2. And the product I1Z I2Z is, please remember, is alpha beta. So it's plus 1 half into minus 1 half, so it gives you minus 1 by 4. So it gives you minus J12 by 4 times alpha 1 beta 2. Okay. Now, there are 2 more energy levels for beta 1 alpha 2. So the Hamiltonian on beta 1 alpha 2 gives you remember this is beta 1, therefore minus u1 becomes plus u1 by 2 because I1Z. So it is plus u1 by 2. But this is alpha, so alpha and I2Z is a minus a half, so it gives you, sorry, plus a half, so it gives u2 by 2, doesn't change. The product is, of course, minus j12 by 4, because it's plus a half into minus a half. And the last is, of course, beta 1, beta 2. You can see both these give you minus a half, and then the product of 2 minus a half is plus 1 by 4. So what are the energy levels? Those are the 4 energy levels here. E alpha 1 alpha 2. This is E alpha 1 beta 2, which is here. This one. Okay? And this is E beta 1 alpha 2. This is the one. And then E beta 1 beta 2. So the 2 green things are the spin 1 transition because it is alpha 1 to beta 1. Alpha 2 to beta, alpha 2. Beta alpha 1 to beta 1. Beta 2 is beta 2. Therefore, if you take this energy and subtract this, you get 1 spin transition. If you take this energy, subtract this energy, you get spin 1 transition. That's what you have. Delta E1 is E beta 1 alpha 2 minus E alpha 1 alpha 2. Those are here. So if you take that difference, it is mu1 minus J1 by 2. You take the second difference, the green one. This is the green one. This is the second green one. Delta E2 is E beta 1 beta 2 minus E alpha 1 beta 2. And that, if you subtract from these expressions, you get u1 plus J1 by 2. Okay. So if J is 0, it's only one frequency. That means the whole thing is collapsed to two lines. If J is not 0, there are two frequencies, U plus J by 2 and U minus J by 2, which is what you saw in the spectrum in the previous lecture, or in the beginning of this lecture. So the same thing, both spin 1 and spin 2. You do the same calculation for spin 2, you'll get the same answer. Instead of nu1 plus or minus J1 by 2, you will get nu2 for the spin 2 plus or minus J1 by 2. Okay? So both lines are split. Now, if you do n equal to 3, slightly more complicated, there are 3 spins. This is the Zeeman term. The spin 1z, spin 2z, spin 3z. H bar omega naught is there, the magnetic field is here, so this is U1, this is U2, U3, sorry, this is 2, okay, not 3, that's a mistake here. And then you have 3 J's, I1 and I2, I1 and I3, 1z, 3z. This should be 1z, 3z, I should change that, this is 3z, and then you have 2z, 3z. So there are 3 terms. And how many states? 8 basis states are there. Alpha 1, alpha 2, times alpha 3. Then alpha 1, alpha 2, times beta 3. You can see that. So, if there is a change in energy between this and this, that is a beta 3. That is alpha 3 to beta 3. So, there is a spin 3 transition. Then, with alpha 1, alpha 2, you have both alpha and beta 3. The next is alpha 1, beta 2. Alpha 1, beta 2 to alpha 3, and alpha 1, beta 2, beta 3. So this is another transition of spin 3. Please note. The spin 1 and spin 2 states don't change. Okay. Then you have beta 1, alpha 2, and then beta 1, alpha 2 with alpha 3 and beta 3. Therefore, you have one more transition for spin 3, which is beta 1 alpha 2, beta 1 alpha 2, alpha 3 to beta 3. Okay. So if we start looking at it, if we start writing the energy levels, these are the expressions. I think what I told you how to get it. You must apply the same rule to get all these various numbers. And if there are mistakes, you should write to me. Okay. Now if you draw the energy level, this is interesting. 8 energy levels are there. Alpha 1, alpha 2, alpha 3. This is beta 3. This is the smallest chemical resonance frequency. Therefore, the energy level is slightly up. The next one is for the second spin, which is slightly bigger in energy, higher in energy. Therefore, it's alpha 1, beta 2, and then you have beta 1, alpha 2, alpha 3. And so you can see 1, 2, 3, 4, 5, 6, 7, 8 energy levels. Now, look at all the blue levels, blue lines. Look at all the blue lines. It is only spin 1 which is changed, alpha 1 to beta 1. Beta 2, beta 3, beta 2, beta 3. So there is no change. Therefore, this is a spin 1 transition energy. This one, alpha 1, alpha 2, alpha 3 is beta 1, spin 1, alpha 2, alpha 3. They don't change. So this is spin 1 energy. This is spin 1 transition. This is spin 1 transition. And all the green ones are spin 3 transitions. You can see alpha 1, beta 2, alpha 3 to alpha 1, beta 2 to beta 3. So alpha to beta 3. So this is a spin 3 transition. So all the green ones are spin 3 transitions. All the red ones are spin 2 transitions. So I'm missing something. Did I miss a spin 2 here? Did I miss a spin 2 transition? Can you tell me where it is? See, blue arrows are 4, red arrows are only 3, green arrows are 4. So why red is only 3? Where is the fourth one? Here to here. Here to here. What do you have? Beta 1, beta 1. Alpha 2 to beta 2. Alpha 3, alpha 3. Therefore, this is the red one. I did not mark it. Okay? So if you look at the spin 1 transition, there are 4 transition energies. These 4. Spin 1 is this one. So you take this energy minus this energy. You take this energy minus this energy. You take this energy minus this energy. Take this energy minus this energy. There are 4 of these. And if you calculate them, you will see they are U1 minus J1213, J1213, J1213. Now, if spin 2 and 3 are identical, then spin 1 connects with 2 and 3 with the same constant. Spin 1 with 3 and spin 1 with 2. They are both the same. If you put that, you will see that there are only 3 transitions for spin 1. U1 minus J12, U1 and U1 plus J12. 2 of them will become the same. These 2 will be different. One will be nu minus J, the other will be nu plus J. 2 of them will become nu themselves, because if J's are the same, this cancels out, this cancels out. So you have 2 transitions with nu is equal to 0. There is no split between delta nu is 0. And so you have 1, 2, 1. Corresponding to the fact that the spins 2 and 3 are identical. Therefore, coupling of spin 1 with 2, coupling of spin 1 with 3, they both have the same J. And if you substitute that in this expression, you get this number. So you get U1 minus J12, U1 plus J12. So the transition of a spin 1 is split into a U1 minus J1, unsplit to U1, and another one U1 plus J. Okay. So this is the magic behind the spin angular momentum energy level calculations using simple first order perturbation theory. You do the same calculation. If instead of spin 1, you want to do this for spin 2. The only thing that you should do is that spin 2 coupled with 1 and spin 2 coupled with 3. If they are the same, then spin 2 sees 2 identical spins this time. So you must make 2, 3, J2, 3 should be the same as J2, 1. You make that substitution, you will also get 3 energy levels, namely U2 minus J, U2 and U2 plus J. And the same thing happens with spin 3. You can carry this exercise for 4 spins. Challenging exercise. I want you to try it out and say how many lines you get. You will get 1, 3, 3, 1. Beautiful. Okay. If you make the correct connections of the J approximations. Okay. So this is all exact angular momentum algebra for first order perturbation theory. Now, the other more difficult one is when you cannot approximate this quantity. Which one? Let's go back to the beginning. This quantity, I dot I, spin I, dotted with spin J. If you write the full terms, it is IIX, IJX, IIY, IJY, IIZ, IJZ. All 3 are there. We were only considering the Z. But now if you consider the X and Y, and you replace them using raising and lowering operators for the JX, IJ, IIX, IJX plus IIY, IJY becomes 1 by 2 times this. Now, you have to solve this problem. This is no longer a simple eigenvalue problem because the states alpha beta are not eigenstates of this operator. I plus changes beta 1 to alpha 1, alpha 2 to beta 2, J minus. If it is 1 and 2. If it is 1 and 2, you see that J1 minus J2 plus changes alphas and betas. Therefore, H on alpha beta does not give you the energy times alpha beta, but gives you something else. So it's not an eigenstate. Therefore, you must write a Hamiltonian matrix for that, and the Hamiltonian matrix should be diagonalized. Okay? Let me just write that down. You must write a Hamiltonian matrix for the 4 states, and a Hamiltonian matrix calculation I will ignore right now. but the Hamiltonian matrix will have 4 by 4 matrix with one 2 by 2 matrix which is off diagonal. You can see that. This is an eigenvalue for the Hamiltonian. This is another eigenvalue for the Hamiltonian because you see it's not connected to any other energy level. Whereas these two are energy levels which are connected. So to get the eigenvalue, you will solve this as a circular equation and obtain the eigenvalues for that. When you do that, you get the energies for 2 and 3 for these two in terms of u1 minus u2 whole square plus j square. And one will be with the minus sign minus j1 by 4. The other will be plus the half with the minus j by 4. So you get different energy levels. Okay? So there are 4 energy levels, and the 4 energy levels are E1T, E2, E1 to the transitions corresponding to that are E1 to E2, E2 to E4, E1 to E3, E3 to E4. And draw the energy levels once you solve for the eigenvalues. It's slightly more mathematical, but I will leave this to you for you to find out. If you can calculate all these energy levels, you will see that the spectrum looks like the delta E1 here, and a delta E2 here, and then there is a 260 minus J12 where C is the spectrum, the square factor method. Okay. Either it gets added or subtracted, and so you can see if it is this side, it is minus J12 minus C. If it is this side, it is minus J1 by 2 plus C, so that the difference is 2C minus J12. So you get that spectrum. There is a very large set of these kind of relations between 2 spins. You can only do this for 2 spins. 3 spins, when you try to do this, the matrix becomes 3 by 3. Sometimes it's an 8 by 8 matrix, but there will be 3 by 3 blocks. And 3 by 3 blocks, the eigenvalues are hard to write out. Therefore, one does this numerically. And if it is a 4 spins and 5 spins, of course, it's not analytically possible. So, what's the summary? If both these nuclei here, AB, here, AB, if both the nuclei have exactly the same combination, then U1 and U2 are identical. Okay? U1 is equal to U2. And then you have a J. You can see that when the 2 spins are identical, the spectrum is that of A2. A2 has only one light. J cannot be observed in that light. Okay. A2 has only one light. When U1 and U2 are identical, you can see this goes away. Okay? This becomes minus 1/2 J12, minus 1/2 J12, and this becomes minus 1/2 J12 plus 1/2 J12, so that goes to 0. This goes to 0, and this is plus 1/2 to minus 1/2 J plus 1/2 J12. So this is plus J, and U1 and U2 are the same, so it is U plus J, U minus J, but the J cannot be observed. Okay? So the spectrum arising from A2 is a spin 1 transition. A2 corresponds to now only 3 energy levels, 1, 0, 1, 1, and 1 minus 1. So 2 angular momenta spin a half. If they are identical, then the 2 give you a triplet and a singlet. You have seen that in electronics because 2 electrons. 2 electrons in the excited electronic state, the 2 electron spins can be added to give you 1. And in that case, there are 3 states for the spin 1, which is the triplet state. And then the 0 state is called the singlet state. Same thing happens here. And the spectrum is that of A2. And so you cannot see anything other than only one line. J disappears from your experiment. So A2 is the limit, AB is practical, you can see in the spectrum. AX is beautiful, which is what you see in all the NMR spectrometers. Okay. Then your molecule, there are a few things I would like to read, which are important for you. Of course, Edwin Becker, High Resolution NMR Theory and Chemical Applications, is an important textbook. Some of you can try to find out if it is available on the internet, and you can see if the copy can be accessed. And then there is the other book I mentioned, that I mentioned was Harold Gunther in the earlier lecture I showed you. These are books that you should look for and try to find out if you can read, and you can get the book copies, and then you can read things out of the book. Okay? These are very, very good books. Of course, our own faculty colleague, Professor Sunder, has published a beautiful NMR spectroscopy, high resolution NMR, but it is slightly more advanced than what I can do here. Okay? So there are good books from professors here as well. Okay? Now, what is important is this line: spectrum arising from a system of nuclear spin that includes one or more magnetically equal nuclei is independent of the spin coupling between nuclei within the magnetically equivalent system. So, AB becoming A2 is a magnetically equivalent system. Therefore, the coupling between A and A cannot be seen. That's what this states. Between nuclei with a magnetically equivalent set will form, if there are three spins which are magnetically equivalent, they will form A3. And A3 is a spin 3 halves and a spin 1 half, 2 spin 1 halves. Therefore, you cannot see again the J's between them. So, angular momentum coupling and angular momentum theory tells you when two spins are strongly interacting with each other, depending on the chemical and magnetic equivalent nature, you can call them as a net spin or as two equivalent spins. Okay? So the spectrum, for example, of A3B does not depend on what is the coupling between A and A, because A3 means three A's which are magnetically equivalent. So B will see only one A, okay, and one coupling between B and A. It will not see BA1, BA2, BA3. There are three A's here. So you can call it A, A prime, A double prime. Then BA, BA prime, BA double prime. You can't see that. You see only one BA. So you can see that the spectrum AA prime, BB prime is, you can see JA prime because A and A prime are not magnetically equivalent. A molecule in which all coupled nuclei have the same chemical shift gives a spectrum consisting of a single line. No splitting. When all coupled nuclei in the molecule are chemically equivalent, they are also magnetically equivalent as they are equally coupled to all the nuclei. But you have to be careful about this. Okay? This is about the spin coupling, the mathematics of it. And I know this is something that you probably have not done in this pattern. Has anyone done this before? This kind of algebra in physical chemistry, in your, okay. But does this somewhere get you an idea that where the AB, AX, AA prime, BB prime, what these things mean? They mean relatively how the spins interact with each other and what environment that the spins are in. If they are in the same chemical environment, they both have the same chemical shape. Then you can't see the coupling between them. But if they are magnetically inequivalent, you can see coupling between this and the other nucleus, and you can see that difference. So this is a standard, what you call first lesson in NMR spectroscopy on the interactions between spins. Weak, these are called weak interactions. The AB spectrum is a strong interaction. The scalar coupling requires all the three terms of the JJ, JX, JY, and JZ. Whereas the AX spectrum does not require the JJ, X, Y, and Z, only JZ, JZ. And JZ is easy because the states alpha and beta are eigenstates of the operator JZ, but they are not eigenstates of the operator JX and JY. This I did that in the previous lecture. I told you that the X component for a spin and a half is 0, 1, 1, 0 matrix. If you remember, Pauli spin 1/2 matrix. That 0, 1, 1, 0 matrix tells you that the X component is not an eigenstate, it's an off-diagonal matrix element. And likewise, the Y component, you would have seen 0, minus I0 for the Pauli Z component, the Pauli Y component. I'm sure you wrote this down. And if you see that, they are also not eigenstates. Only Z component is the eigenstate of the alpha and the beta. Therefore, Z terms are easy to handle, but the X and Y terms require solving this as a matrix problem of matrix eigenvalues, like we do in quantum mechanics. But the problem is these matrices are smaller dimensional matrices. Even for many spins, I handled with 2 raised to n when n was more than 6 or 7 in dipolar interactions. The matrices that I can handle very large, but still they are smaller than what quantum chemists actually do these days in terms of thousand by thousand matrix or million by million matrix that they solve the eigenvalues for. But they do it using Gaussian and other quantum chemistry programs, numerical programs. Okay? So this part of the spin interaction is extremely important. The last part of today's lecture, if I have 5 minutes, I will tell you that there are different Hamiltonians, spin Hamiltonians, which you should be familiar with. So let me see if I have that lecture. Let me just check to see. And I will also share that lecture with you for you to go through. Oh, I guess that. I have that, yes. Okay, so this is everything about the MMR, both liquids, solids, and the interfaces and so on. So this lecture is a very short lecture. Tells you what are some of the important Hamiltonians, and particularly for solids, okay, NMR spectroscopy. So the nuclear spin interactions in solids, solids in the sense, spin 1/2, which are there in solid lattices. Nuclear spin interactions in solid can be classified as 2 things. External field, the magnetic field that the spins interact with, and then interaction between the spin internal fields, or interaction between the spins. This doesn't depend on the external magnetic field. So, and then there is also the radio frequency field, which is the time-dependent field that raises or lowers the energy. That's the field which probes the transitions. So the RF field. The RF field depends only on the X and Y components of the spin with the RF field frequency. So the RF field is written as minus h bar for every spin in the solid, different from the other. There is a corresponding absorption frequency omega 1i for the RF field, and then the X component and the Y component oscillating in cosine omega t and sine omega t. That is why it is called radio frequency oscillatory magnetic field. That's important for giving any transitions. And then you have the chemical shift Hamiltonian. Then you have the spin-spin coupling Hamiltonian. You have something called the quantum pole Hamiltonian. And then you have the HS, which is a spin rotation Hamiltonian. The molecule rotates and the spins also associate with the overall rotation. So this is called spin rotation. And then you have the HL, which is the spin lattice interactions. Now, these are the most difficult to handle. The spin lattice interactions essentially kill the magnetization over a period of time. Therefore, they are basically what is called the not oscillatory type. They are decaying contributions to the overall component. So there are many of them. So when I told you chemical shift, we said 1 by the sigma, and then we wrote. But the chemical shielding is actually dependent on 9 quantities. The sigma actually is defined as sigma x, y, x, z in Cartesian coordinates, and x, y, and y, x are the same, x, z, and z, x are the same. Y, z, y, and y, z will be the same. And what you measure experimentally is the sum of the 3 components, sigma xx plus sigma yy plus sigma zz, the sum divided by 3 is what is called the scalar shielding constant that you use in your NMR spectrometer. But if it is a solid, there is also a component called sigma xx minus sigma yy, which is non-zero, and this is called the anisotropic component, not isotropic. Isotropic means all 3 are the same. Xx is equal to yy is equal to zz. That's not what we have in a solid. The xx is different from yy and different from zz. Therefore, for a solid, we have both isotropic chemical shift, which is this, and the anisotropic chemical shift, which is the difference between the 2 components, xx and yy. That is, sigma is known as a second rank tensor. And likewise, the tensors are physical quantities in real systems. We do have the measurable quantities represented by vectors, represented, the energy is represented as a scalar, angular momentum is represented as a vector, and dipole moment is a vector, but the quadrupole moment is a second rank tensor, and the octupole moment is a third rank tensor, and so on. So there are physical quantities which are represented in different ways in mathematics. And there is also the most important thing called the dipole-dipole interaction. This is the only thing I will spend the time on. When 2 spin magnetic moments in solids are fixed like this, they interact directly, and the interaction between this magnetic moment mu1 and magnetic moment mu2 is given by this formula. Okay? If the distance between the 2 spins is r, you can see that the dipole-dipole interaction is the scalar interaction between the magnetic moment I dotted with j divided by r cubed, the distance cubed. And then this is subtracted by another term 3 times, mu times rij. So if mu is like this, mu2 is like this, then we'll just stop doing that. So, if we have this, there are 2 mu's, something like this, if they are oriented like this. The distance between the 2 is this rij. Okay? Therefore, this mu interacting in the rij vector multiplied by this muj interacting in the rij vector, that's one product. This mu interacting with this mu is another product. That's what you see in the 2 terms. Ui dot uj divided by r cubed, but then ui rij interaction multiplied by muj rij interaction divided by ri 5 power to the 5. Because you see there are 2 r's here, therefore dimensionally, if this has to be energy, it should be the same as 1 by r cubed. So you have 1 by r to the 5 multiplied by 2 r's, r squared. So it is r cubed, 1 by r cubed. This is the dipole-dipole interaction, which is extremely important, and here is the picture. Okay? So mu I and mu j separated by a distance rij. You can see mu I dot mu j, mu I dot rij, mu j dot rij. Remember that these things can be expressed in terms of the spherical formulas, angles, sine theta cos p, sine theta sine p, and cos theta, like what you have done in hydrogen atom. And so when you do this, the dipole-dipole Hamiltonian consists of 6 terms, A plus B plus C plus D plus E plus F. But the first 2 terms, A and B, are the most important term called the secular interactions. And the formula looks like A is I spin Z component, another spin z component multiplied by 1 minus 3 cos square theta. And you see that this goes to 0 if cos theta is 1 by root 3. Because the cos square theta is 1 by 3. When 3 and 1 by 3 cancel, a will go to 0. And b will also go to 0 if it is 1 minus 3 cos square theta is 0. Therefore, how do you make that 0? You rotate your magnetic axis at an angle to the magnetic field. Okay. At an angle to the magnetic field, this angle, cosine theta, is 1 by root 3. And then you rotate the sun with this orientation. You rotate the sun in this orientation. When you rotate this, all the anisotropic components go away. Only the isotropic dipole-dipole interaction, all the dipole isotropic interactions go away. Only the anisotropic transfer, the CDEF transfer. Therefore, magic angle spinning that you do in solids is to get rid of the two terms A and B experimentally. A and B. You choose the angle theta as 1 by root 3 or cos theta is 1 by root 3 or theta is 54 degrees, 7 minutes or something like that. And so when you do that, A goes to 0, B goes to 0. The bulk of the dipolar interactions is lost. Therefore, in solid state NMR, if you don't rotate the spin sample at an angle, you get very broad spectrum. But if you rotate this, the broad spectrum, which contains all these interactions, narrows down to a very short line and then satellites coming in. And therefore, the whole solid state spectrum is to understand. The narrow line disappears because of the fact that the A and B go to 0. The spectrum is the satellites are the most beautiful things that one tries to study using second order perturbation. So this is for dipole-dipole interactions, and magnetic dipole-dipole interactions are extremely important for various applications of NMR. I will not do this here. There is a separate lecture later on nuclear magnetic resonance spectroscopy that I plan to give. Okay. So at that point of time, you may look into NPTEL to see these lectures have been recorded. But there are other chemists and physicists in India who have given such lectures in the NPTEL website. So if you go look at the NPTEL website for magnetic resonance, for example, let's just do this quickly and share the screen. Just one moment. Yeah, so if let me share the screen. If you go to nptel.ac.in, go to the website, and if you look at the courses, NPTEL courses, and you look for nuclear magnetic resonance, search disciplines, chemistry, and biochemistry. You will see so many lectures are there, so many courses are available for you for free. And you can see that these are all given by different IIT faculty. And there is an NMR spectroscopy for structural biology by one of the foremost experts in India in biological NMR, Professor R.V. Hosur, and his colleague, Professor Raman. And likewise, there is one more NMR spectroscopy lecture, if I remember from IIC back home, which is given by Professor Atreya, I think. Yeah, one-dimensional, Surya Prakash. Yeah, Surya Prakash, Dr. Surya Prakash gives you 1- and 2-dimensional NMR spectroscopy for chemists. There are lots of lecture videos which are available, and you can, these courses are now offered for credit. So if your institute, if your college allows these courses to be taken for credit, you might use this to replace one of the credits that you do in your university. And likewise for optics and spectroscopy, and you can see that there is another course Where did I see? Yeah, ultrafast optics and spectroscopy. There is a Thanos course. So you can see there are many of them. I'm just trying to look at Professor Athreya's course. I thought I saw that. But you can go and check these things out yourself. Okay. Yeah. Then there is also molecular spectroscopy course given by Professor Balakrishna from IIT Bombay. All these things are free for you. Okay. We have worked very hard for the last 25 years. And I know particularly because I was also one of the coordinators working with all the individual professors before for many years to get and get support from so many other agencies to create a full body of chemistry, physics, mathematics, biology, and engineering lectures, which could be useful for you no matter where you are and what you are doing. From all these gurus in your home, you just have to click the YouTube video and start seeing what you want to see. And if you don't understand, write to them. Okay? So let me stop here. It was very nice to meet you the third time. I don't think I will meet you again because the sessions are also coming close. And I wish you all the best. If you have any questions, I will be happy to answer. Okay? I hope that this lecture was an opener. I don't think you would understand all of them as is. If you have not seen them, but it's important for you to go and look at them, read them again in different contexts and talk to your professors about details and try to understand nuclear magnetic resonance spectroscopy as it is one of the most fundamental tools for chemists, particularly chemists, organic, inorganic, and physical chemists, all three of them. Therefore, being very strong in the theory and experiments of NMR gives you a fantastic handle for you to work with all of chemistry. Okay? All of this. Thank you.
Swayam Prabha. Digital India. Educated India.